Hello, and thank you for tuning in to this fast chat on hardening the DevSecOps Toolchain. My name is Daphne Krause. Today I'm speaking with Rampart AI's co-founder, Jacob Staples. Jacob has led many successful research and development efforts in the cybersecurity space. Today we are diving into one of Jacob's many passions. We're discussing how to harden the DevSecOps toolchain and the recent Confluence Atlassian security vulnerability. So Jacob, it's so great to have you here. Can you explain why hardening the DevSecOps toolchain is so important and how it can be achieved?
Thanks, Daphne. It's great to talk with you. And absolutely. So what I'll say first is that dev tools are easy to take for granted because they tend to have this magical property of just working. And I'm putting that in kind of air quotes here. And that's true because otherwise no one would use them, right? Like if something didn't just work, you wouldn't be using it every day. The problem is that these tools have become a bit like other types of infrastructure in that you don't think much about them until they either stop working or until something really problematic happens on the security front, like we've seen with Confluence recently. And that's not just to pick on Confluence, it happens all the time. And I should probably clarify here that by dev tools, I really mean anything that runs in your development workflow. So that's going to range from wikis like Confluence through issue tracking, source control, CI/CD, IDEs, and even low-level things like build tools such as Apache Maven. And in other words, the things that developers have their hands on to make software. For security in dev, it's every bit as important, and I would argue even more so than it is to the apps that you develop with those tools. So, let's suppose that someone who shouldn't gets commit access to your code repository, or someone can mess with your compiler or your IDE. Now we're looking at some kind of a crazy, scary situation, like a SolarWinds Orion type of situation, where even your signed software becomes suspect because you don't have control over the supply chain anymore. That's frightening, but probably the most realistic and biggest immediate threat when we're talking about DevOps tools is the direct theft of intellectual property. And that's a huge deal because it can completely break your business, especially if you have some kind of a proprietary process or algorithm. So your production environment is where your business makes your money. And the importance of securing your dev tools is to make sure that your dev environment isn't where you lose it.
Well, can you explain a little bit more about the Confluence Atlassian security vulnerability and what could have prevented that?
Sure, yeah. So just to be clear, we're talking about the recent CVE. The number is 2021 26084, and I can definitely tell you a little bit about how that specific vulnerability works. And the first thing you should know is that it's not really that much different from vulnerabilities like it that we've seen before. Guess what other library had an exploitable OGNL cross-section? Our old friend, the now infamous Apache Struts. And even though this isn't the same vulnerability that led to the $0.31 or whatever it wound up being check that I don't know if anyone's gotten in the mail yet from Equifax, this has happened before. And the question here is, if something like this has happened in the past, why does it keep happening? And right now, in my mind, there isn't a great answer to that question. And it kind of hints that the current way that we're developing and securing software still has some holes to it. The specific issue that affected Confluence was an OGNL code injection attack. And this thing could pop up when someone who isn't a nice person makes a request to your Confluence instance containing a header property with a malicious OGNL expression inside of it. And if you're not familiar with that kind of thing, basically a header is just a key value pair that clients and servers use to pass information back and forth along with their messages. So for example, a header might be used to specify what kind of content is in a message that I'm making a request with, or what kind of content I'm willing to accept in response. In this case, it was just an OGNL expression contained in a header. And as for OGNL itself, that stands for Object Graph Notation Language, and I could spend a long time talking about that, but I won't really, because a couple of hours would only be scratching the surface there. But at a very high level, just think of it as a miniature programming language that's used by code template engines, things like Velocity. And OGNL really lets you interact with complex server-side code using simple expressions that can be stored nicely in configuration files, or in the case of templating engines, dynamically used in response to requests that the server receives. So basically, long story short, in this case, OGNL is helping your server-side template code return complex responses to the client. The problem with all that magic is that the client side affects the actual OGNL expression that's used by the server. And that means that a bad guy could do something very similar to SQL injection and escape out of an OGNL expression that's used in a template and then start a new one that runs code. And critically, they could do that just by virtue of nothing more than making a specially crafted request. They didn't have to already have some kind of execution foothold or starting point on the target system. And again, that can result in remote code execution. And now the bad folks have reverse shell and they start dropping payloads onto a box where your code lives. And that is obviously really, really bad. As for what would have prevented all that, I want to say that any of the dozens of RASP tools that are out there today should have caught that. And I'm sure that some of them did. But I'm only aware of one tool that would have been able to do that in the hours or the days before that CVE was released. And that is Rampart, which is a technology that we developed at Rampart AI. And Rampart is a learning-based RASP that it doesn't rely on specific fingerprints or behaviors that are known before this kind of stuff happens. What Rampart does is it alerts you and optionally blocks when your app does something that the Rampart agent hasn't seen before. So if your app tries to write to a new file location, that could be alerted or blocked. If your app tries to spawn a new thread in a way that Rampart hasn't seen before, that can be blocked. If your app tries to execute a subprocess via runtime exec, which is the kind of thing that would happen in this Confluence exploit, that's going to be emphatically blocked. And if you're familiar with something called SE Linux, you can kind of think of this like audit to allow, but for the purposes of the internal operation of your application.
So Rampart AI would have helped stop that vulnerability from needing a patch, essentially. It would have caught it before it happened.
That's exactly right. I wouldn't say for a second that you shouldn't patch vulnerabilities, even when you have a technology like Rampart in place. But Rampart gives you an extra layer of breathing room when this kind of thing happens, because it prevents any of those behaviors that it hasn't seen before from occurring in your production environment. So if a bad person made that OGNL payloaded request to your server, Rampart sees that request and blocks the downstream horrible stuff from happening, like using runtime exec to spawn a subprocess. And most importantly, it does that for vulnerabilities and code bases that haven't even been written or discovered yet. And as to how we know that Rampart fixes problem like this, in addition to just saying that it does, we prove this out in a cyber test range. So essentially we throw on our bad guy hats and we use pen testing tools to hammer on vulnerable endpoints. And we show that without Rampart, these things are trivially exploitable. Whereas with Rampart, these attacks are going to fail every time. So that's kind of how we know that we have something valuable here and something that actually solves this problem.
So going back to just talking about patching and the patching culture, we both know that patches come out all the time. So has patching become the protocol for our cyber insecurities? And is there a better way to protect against these bad actors?
What I'll say here is that the way that app security is handled currently, with that mindset, a little bit of, what you're calling insecurity is probably warranted. A little bit of fear and a little bit of uncertainty is definitely warranted. Because our posture is very reactive. So the best case scenario today is that when something bad happens, some poor sap gets a call at 2 a.m. to go update production with a patched version of a library. The worst case scenario, though, is much more terrible than that. And that is that you don't know until 3 months later that all of your IP got stolen and possibly even that your product was used to Trojan into your customer machines. And at that point, app security doesn't matter to you because your business isn't going to exist for much longer. So at Rampart AI, what we're saying is that this after the fact reactive approach that's been taken, this patch oriented approach, it's just not good enough. Instead, what we need to be doing is continuously monitoring what apps are doing and blocking them from ever going off the rails in the first place. And that's something that we believe we are unique in offering to the application security space.
Well, Jacob, thank you so much for your time. And to our listeners, thanks for sticking around. For more information about Rampart AI's DevSecOps solution, head to rampart-ai.com. Until next time, stay secure.